Okay. Okay, now we need to continue, and I hope today I can finish chapter 8, the essential parts in the chapter 8, and we can continue chapter 9 later on this Thursday, and maybe the last 2 or 3 meetings. So let me check my schedule. Schedule is still so today is 23, so 26 will be chapter 9. This is May. And then 30 still chapter 9. And June 5, this will be maybe so chapter 9 and review if we still have time. And I think after this June 5 we can decide whether we need to why this 5 not 5, sorry, supposed to be 2. So I think we can have a break on the 6, so 6 will be break. And 9 will be finals. How about that? So June 9 will be a final exam. How about that? Is that okay for the schedule? So June of 9 will be final exam. How about that? Do you think that's okay?
It's fine.
Okay, I think June of 9 will be a final exam. But if you have any schedule, and maybe you can check later, whenever you find like the schedule is conflicted, maybe having a tight schedule with other course, just let me know. I can adjust our finals. And actually, between 7, 8, we can also have finals because since this is online final exam, we can have much more flexibility, right? Okay, I think we can continue. Okay, psychrometric chart. Okay, what's important in the psychrometric chart? We can also imagine or visualize what we call the adiabatic cooling. So this is practically in the descriptions. What adiabatic cooling means is you will have or you could imagine a gas, okay, warm gas, warm gas that is brought into a contact with a cold liquid. Let's say this is a cold liquid. So the gas will be cooled down. Okay, so gas is cooled down, and some liquid evaporate. Okay, so we could say that heat is transferred from gas to liquid. But there is no heat transferred between gas liquid system, and surroundings. So all this phenomenon is in one system. So it's one system. So this is a system. And outside the system is the surroundings. Okay, so that's the surrounding. So because of this, remember, no heat transfer between the system and surroundings means that we can call this in the terms of adiabatic, right? Okay, so that's what the adiabatic cooling means. So the system is cooling down, but the heat is transferred only inside the system, not outside. Okay. And some of the process that is describing this adiabatic cooling is first is spray cooling. I will just write some of the terms, and then spray dehumidifications, and then drying, and then spray drying. So I think you can check each of these statements or the terms mean, and I think it's not really complicated. And as long as you are focusing your phenomenon on what is happening in this general adiabatic cooling, I think it should be fine because this 4 is basically a common process for adiabatic cooling. So this is a common process. Let me just write common process in adiabatic cooling. Okay. We can also explain this adiabatic cooling or the process inside with the picture on this wet bulb temperature line. So if you could imagine this, we have relative humidity when it's 100%. And imagine we have this temperature. So air is undergoing the adiabatic cooling through some contacts with liquid, or let me write here. So air undergoing adiabatic cooling through contact with liquid water, and it's moved along a constant wet bulb temperature line. On Cyclometric Chart, from initial to 100% relative humidity. So suppose the T1 is our temperature that we are measuring. So this will be our inlet air. We have the constant wet bulb, and we goes through, take this constant line until we getting into this humidity 100%, and this will be our wet bulb temperature. And further cooling, it will lead to condensation, and then the humidifications. Okay, so I think it will be best to be explain through the I haven't. Okay, so it's best to explain through. I believe you have heard some device that's called the humidification. The humidifications, and that is works based on how they are measuring the system, um, the temperature, and then the moisture of the environment, and they will then compress, let's say, compress the air and then make it into water and make it into a condensation. All right. Okay. Okay. I think we can go to the next. So adiabatic cooling, cyclometric chart, adiabatic cooling. What else? I think we can go to the next sections. Let me check. Oh, I think we can move to another another point of view. If we have a spray tower, for example, we have a stream with this temperature and 10% relative humidity. They are humidified in a adiabatic spray tower, and they operate in, the pressure is 1 atmosphere. The emerging air is having this 40% relative humidity. Okay. The question is asking the absolute humidity and adiabatic saturation temperature of the entering air. Use the cyclometric to calculate the rate at which water must be added to humidify this flow 1000 kilogram per hour of the entering air and the temperature of the exiting air. So first, a little assumptions that we might need to take here is assume heat required to raise temperature of liquid in spray tower is negligible because it's very small. The heat is very small. Negligible compared to the heat of vaporizations of maybe water, right? So by doing so, we are actually assuming that this is works based on adiabatic saturation curve. So we are just looking on the cyclometric chart. Okay. Cyclometric chart, cyclometric. Okay. So based on the cyclometric chart, we can confirm later on. Or if you would like to see the 30 degrees Celsius, so here's 30 degrees Celsius. And then relative humidity is 10%. Wait, is 10%? Humidity is this 10%. So this will be the line. So you could have this, and then we could have the moisture. We get the moisture, and we get the the wet bulb temperature, right? Wet bulb temperature. It's around 13. Okay. And the moisture is around 0.002 something to 6 to 7. So okay. So we could write that as our humidity and the wet bulb temperature. So based on the cyclometric chart, So based on these two components, we have the absolute humidity is 0.0026 kilogram of water, dry air, and wet bulb temperature is 13.2 degree of Celsius. This is, we can call, based on what we have defined here, this one, we can call this is our adiabatic saturation curve. Okay, so the wet bulb temperature in the cyclometric chart, we can say that that's the saturation curve. Okay, so we can also say that this is our temperature or our adiabatic saturation temperature. Okay. Okay, this is for number one. Number two, use cyclometric chart to calculate blah blah blah. Okay, the state we can write, since the wet bulb is 13.2 degrees Celsius line, we have the wet bulb line. It's intersect with HR equal 40%. If we check the wet bulb, if you check the wet bulb, we can see that it's intersect at this 40%. And if we check that the 0. Oh, sorry, wrong. From the intersection in this line not this line here, go here up until here, and then what is the 40%? This line. Oh, wait, let me erase this. Wait a minute. Must be added the temperature of the exiting air. Okay. Relative humidity 40% is this. Oh, supposed to be the exiting air, right? Exiting air. Okay, so we get that. Let me write sec with the absolute humidity, or HA, for the exit gas. Zero 0.0063 kilogram H2O kilogram of PA. So the mass of the dry air, the flow rate, this is air, and 1 kilogram dry air, and 1.0026 kilogram air. This is from this plus 1. This is 1 plus 0.0026 kilogram. So basis is 1 kilogram air. So the flow rate for the DA or the dry air is around 997.4 kilogram DA over hour. And then the amount of water is basically 7.4. This is the difference between the 63 and 26. If you calculate this, this will result on 3.7 kilogram water per hour. And also from the figure, we see that this 0.00 0.062 is here. It's around here. So you get this around 21 degree. 21.2 degree. So temperature is 21 point. Okay. So basically, first the idea is to get the wet bulb temperature. That is our temperature for the substance to be saturated, and then from there we are going to find the moisture. Okay, so basically the water that we need to add is based on the difference in the moisture. Okay, the difference in the moisture, the humidity absolute. Okay, so okay, I think the last sections is about the heat solutions, heat of solution and mixing, and and the enthalpy concentration chart. So for enthalpy concentration chart, it's similar to what we have in cyclometric. So we need to configure through some to some graphs, some curves. I think we can go first the heat of solutions. We will go back to the cyclometric chart if we have time, and I think I will just add some additional later on. Okay. So the next part is the heats of solution and mixing. So it's stated by this delta H S, some point T and some R, some mole. We define this as a change in enthalpy for a process in which 1 mole of solid is dissolved in R moles of a liquid solvent at constant temperature. The solute can be gas or solid. So as the R becomes large, the delta HS approaching, we call the limit of value. We know that this name is heat of solution at infinite dilution. So heat of mixing this means that heat of solution when the process involves mixing two fluids rather than dissolving a gas or solid in liquid. So in general, okay, let me just write in general. So enthalpy of a solution containing R moles of H2O per mole solid is for reference states of pure solid and solvent at 25 degrees Celsius and 1 atmosphere. So what does it mean is we could write the enthalpy as the delta H as at some condition of R. Okay. And simply we could write this as minus delta HS when the moles are large. This is for reference states of pure solvent and infinitely dilute solution at 25 degree and 1 atmosphere. So this enthalpy, these two enthalpy expressed as uh, per mole of solute, okay, not solution. And how to find the heat of solutions, you can check the table B11. So check table B11 for heats of solutions, 25 degrees Celsius. For some, yeah, for some solution, okay, like natrium hydroxide or the sulfate, you can check the table B11. And you can check also they are having difference in R, in moles. Okay. So when we are applying this heats of solution, if we have the mixing, if we have mixing, and we know the solute, we know the solvent, we may apply this table B11. Okay. There are some example, but I will just skip that for now and maybe directly go to the enthalpy concentration chart first. Okay, and then later on I will just filling all this the skip parts. Okay. Okay, wait for a moment. Okay, sorry. Okay, now the enthalpy concentrations chart. Okay, so especially for the single liquid phase, we will observe. Okay, so if let me check. Okay. This is enthalpy concentration chart for the sulfate and the water. As you might see from what we have here, it's basically uh, divided by the axis is the fraction of the sulfate, and this is the enthalpy, and it's they are using the British units, so you need to be carefully observed. Okay, so it's on the Fahrenheit, okay, and the enthalpy is in BTU and pounds, and what we have here is basically the temperature they are working on. Okay, so you have the difference in this temperature. So depends on the temperature when we are working. We can design or we can decide how much enthalpy we need. Okay, how much enthalpy we need. Okay. So basically, if you have the if you have the mass fractions, for example, maybe 0.5, and you want to have maybe in the 77 Fahrenheit, maybe up until here, then you have the enthalpy that you might need, and carefully looks on this freezing lines. So we will have the enthalpy for freezing and enthalpy for the liquid part. Okay, I think I will just give you in the additional example and maybe additional videos for this part. Okay, another thing aside from this enthalpy concentration chart for this sulfate, we also have the vapor liquid equilibrium. Okay, so I will explain later for the part, but let me just give you a brief through the enthalpy concentration chart for vapor liquid equilibrium calculations. Okay, now this is the graphs, and it's also using the Fahrenheit and the BTU, so it's a British standards unit. And we have the reference states for both. So this is for ammonia and water. So they have different temperature for their liquid form. So if you look at this point, so B, A, and C, this means that we will have a proportions. We will have proportions that is based on the phase that is in the graph. So we will have a liquid phase. So liquid phase and the vapor phase. Okay. So if we would like to evaluate what is the A, we could see from the triangle. Okay, so we could draw a triangle here. So maybe drawing in the sides here. I think if you're familiar with the phase diagram, this is the same phase diagram that you have learned before. So let's say this is B, A, and then C. Okay, and this is the liquid, right? This is the liquid. This is the vapor, and this is the fraction that is in the middle. And we know that we can have a proportions, liquid, vapor. Okay. Basically, what we have here, this and this. So we call this as the lever rule, the lever rule, like in the lever as in the cantilever. And depends on which part that you are going to evaluate. So F is a total mixture. This is the liquid phase. This is the vapor phase. Okay, perhaps I think we still have time. Let me just add what can we do from this vapor liquid equations here. So let me just add Oh, not this one. Equilibrium flash vaporization. So we have a 30% weight of ammonia at some pressure. It has a rate, flow rate, pressure, 1 atmosphere, enthalpy of the phase solution relative to the reference condition used to construct. So we have the figure here. I think we can erase this first to make it easy to calculate. The vapor composition is 89 weight% of ammonia. The vapor, right? The vapor. And it depends on the temperature of the stream. The mass fraction in the liquid product, flow rates of the liquid and vapor product stream, and the rate at which heat must be transferred to the vaporizer. So, do we have the picture? Oh, I forgot to put the picture. Okay, let me just draw quickly. So we have a tank here, right? Tank. And we have the input stream that is 100 lbm per hour. And we have 0.3 lbm, right, of NH3 over lbm. This is the mass fraction or the weight percent. And the enthalpy is 100 BTU over lbm. We have some coil that is going to relate to the heat flow. That is the questions, right? And we have the mass in vapor and mass in liquid. And the vapor have the 89%, so 0.89 lbm. So 0.11 lbm of H2O by the fractions. So we might have the specific enthalpy for the vapor. Similarly, on the liquid, we need to find this fraction on liquid. And for the water, and we might find the enthalpy for the liquid. Now from the figure, if we have the 0.89, so we have, will be around here, right? Around here. So yeah, assumptions, we need just to take the temperature is 120 Fahrenheit. Okay, so temperature is 120 Fahrenheit, and at this 120 we could find the fractions. That is for the liquid, we take this line up until here, right? So this would be, you can say 0.2, or if you want more precision, as in your textbook, the fraction for the liquid will be 0.185 lbm. So the specific enthalpy for liquid is around, this is around 50 or 45 BTU over lbm, and the vapor is around this. Okay, this is around 700 something. So this is around 728 BTU over LBM. Now finding the flow rate, we are going to use the lever rule. The total is 100 LBM, so we could find through ml over 100 LBM over hour. This is xv minus xf divided by xv minus xl. So from here we get the ml is 84 LBM per hour of the liquid. And for the vapor, this is just 100 minus 84. This is a 16 LBM per hour of vapor. And then the energy balance, we could just take this and the vapor plus the liquid, because it's the outstream, but the output, minus the total. The total is 100 and then HF. HF is this, right? This is one HF. Okay. And all the M, H, M, H, all we have in the informations. M is this, H is this, and we can calculate all the calculations here, and this is about the 5,400 BTU per hour. Okay. So basically, as long as you understand how to use this triangle, the lever rule, I believe there will be no problem at all for our calculation. I will just give you more examples later on. But for chapter 8, the essentials is finished. So we end the chapter 8, and we will move on to chapter 9. And if there is anything that I need to add, I will add in the additional videos, as in some examples on this part, and also some examples on this part. Okay, I will add in the additional videos. Okay, so hopefully I can add the additional videos on hopefully this weekend. Okay, I will add the additional videos. Okay, so next Thursday we will go. So next Thursday, so 26, 5/26, we'll be starting chapter 9. Okay. And 5/30 still also chapter 9. And also June, wait, June 3rd. That's supposed to be holiday, right? Or no? Oh, June 2nd. June 2nd is supposed to be holiday. Is that correct? June 2nd. So we still have at least one more class. But I will give to you whether we need to. It's up to you actually. I think 2nd of June is that holiday, right? Can you check it? If this is holiday, do you want to have a class for this 2nd of June? If not, then I will just prepare additional videos for additional part on chapter 9. Perhaps just an example, because chapter 9, I think not as much as 8. 8 is, I think, a little bit much. Okay, I think just videos. I think I just add videos. I think just adding examples on chapter 9. That's what my plan for 2nd of June. Okay, if there's no questions, for the quiz, I have checked some of you. I think it's okay. What I want you just to make sure is, because I will also use the same platform for the final exam. I think for Rifaldo and Chantong, I will let you know the system, because I think the problem is just two of you, because the other students not having a problem. So I need to check all the system, or maybe we need to have some conversation after the class. Okay, maybe I will just email you or just line you. Okay. So I think we finished up until here, and hopefully you can review the lectures. And um, actually, I'm still looking for chapter 8 quiz, um, since we have a really tight schedule, I think. So chapter 8 quiz. Yeah, chapter 8 quiz probably this weekend. Okay. But I will give more days for you to have, maybe 4 or 5 days. So hopefully that's enough. And while doing that, I will just checking your system. Okay. So if there's no questions, I will just stop until here. You can leave the meetings if you want.
Thank you, bro.
Yeah, you're welcome. You're welcome. Oh, QR code. Sorry, sorry. Here.